Hey everybody, we're going to start one last review for the night. Sorry, my other channel. One last lecture for tonight. And in fact, we are going to look at a very basic alkylation through enolates and enols. All right, so what we're going to talk about today is this sodium hydride, so acetaldehyde, sodium hydride, and let's say 1-bromopropane, and what we're going to get out of it is this. 1, 2, 3. We're going to go from acetaldehyde to pentanal. So let's look at the mechanism here. Now to start with, we're going to do this through the enolate pathway. You'll remember, hopefully, since we just talked about it, for me it was 10 minutes ago. Whoops, let me do this correctly. The acetaldehyde is going to provide the proton. The hydride from the sodium hydride is going to pull it off. And your enolate forms thusly. Now, this is where the book and I have a major difference of opinions. This is the preferred form of the enolate. This is more stable. The book, however, presents to you that they want to list it always like this. Frankly, they are exactly the same molecule, they are exactly the same anion, and if it were on any other subject than this, I wouldn't care. However, the difference here, what bugs me, is the fact that if you go all the way back to the early days of 325 and pKa, you'll remember that oxygen has a negative charge much better than carbon as a negative charge because of electronegativity. So because of that, I prefer the enolate, what I call the true enolate form of the anion, which is the negative charge on the oxygen and the pi bond between the two carbons. The book prefers it like this with the negative charge on the carbon. I'm going to continue to use the top example because that's the one that I think is right. However, if you use the one that the book uses, which is the example in, what is that, orange? The example in orange there, I can't knock you for it. Just be aware that I'm going to be using the enolate form. Okay, so there's our 1-bromopropane. Here's how the mechanism works. Reform the carbon-oxygen pi bond, break the carbon-carbon pi bond, and those electrons will do a nucleophilic attack on that primary alkyl halide and knock off the bromine. So what we get is the pentanal like we have there. Now let's, just for the moment, do it like the book does. And that is, with this anion, here we go here, bang, bang, and what we get is, and I have to write really small here, the pentanal. Either way, it's fine. I just want you to know the way that I'm going to do this. Now, let's take a slightly closer look at this mechanism, particularly through the enolate form, because this is kind of important. So important, I'm even going to bother to draw it correctly. Ooh, wouldn't that be a shift? Realistically, on this enolate, there are two possible sites for nucleophilicity. One of them is the nucleophilic carbon, which is what we used in the last example, and the other one is that oxygen. Now, if we go with the nucleophilic carbon, which, by the way, is the right way to go, we go and we wind up here. and all is right with the world. However, if we decide to use the oxygen as the nucleophile, what you would get is here. Now, this is where things can get a little bit squirrely, because I just got done telling you oxygen's better with a negative charge, blah, blah, blah. And that's true. But what we make down here in the orange is a vinyl ether. And vinyl ethers are unstable. Pretty darned unstable, actually, which is another one of the reasons that whenever we see nucleophilic attack, we see it through the carbon of the enolate, not the oxygen. Okay, now this was the enolate way to do this. The follow-up question would be, is there an enol alkylation? And the answer to that is yes, but you must use acid. Now, bear with me on this one. So here's our acetaldehyde. Oops, sorry, forgot my own habits. Let's draw it out this way. We've got hydronium, usually from sulfuric acid, and we're going to go with butyl bromide this time, 1-bromobutane. The result, what we would get out of this is 1-hexanal. So let's take a look at the mechanism as to how. Because this is an acid pathway, the first thing we're going to do is protonate your protonate your carbonyl carbon, which gets you here. And now we use water to deprotonate and give you the enol. Yes, the enol only exists in some fraction of a percent, but if it exists at all, we can use it. And in point of fact, here's what happens. Carbon-oxygen pi bond reforms, nucleophilic attack, knocks off the bromine, and we get, well, bollocks, I'm out of room. Not quite there yet. We get this. Where all we need to do is remove the proton, and we have our final product. Now, this is not going to be some weird example of which one of these will work, because they both will. They will both work. But there's a quirk that goes with each of these. Let's examine what happens if we have an asymmetric carbonyl to start with. Let's say we have this. 2-butanone. Or methyl ethyl ketone. And we're going to be doing this through a base pathway. If you're looking at that structure and you're saying, hey, I see 2 possible enolates I can get out of this, I'm going to be saying, hey, guess what? You're absolutely right. So let's take a look at what those are. One of them, if you remove the orange proton, gives you this enolate, while the blue proton, realizing they're not actually orange and blue, who knows, they may be, we can't see that small. I like to think of my subatomic particles as being very fashion forward, thank you very much. So we wind up with these potential 2 enolates, and the next question, as those of you who know me should be, which one of these is going to predominate? And hopefully the answer should be obvious, that it will be this enolate, that predominates because the carbon-carbon pi bond is more substituted. In fact, that can even be extended to, let's go back to our original question, which I think was this aldehyde with, I'm going to say sodium hydride, and I think it was 1-bromopropane. The product here, 1, 2, 3, is that, correct? But my follow-up question is, if you have any extra hydride lurking around, won't this occur? And here you'd have this as your enolate. And the answer to that is, yes, if you had extra base sitting around in there, this would indeed be an enolate that you would form preferentially, because in terms of stability, this enolate is less stable than this enolate. Simply because when you actually form the enolate structure, the pi bond is more substituted. So, no matter which way you go with these, overreaction is always a possibility. Now that's it for tonight. Tomorrow, we're going to talk about this a little bit more, acid and base pathways for these sorts of reactions, and some other fun things we get to do with alkylation. So, everybody, stay healthy, stay safe, stay cool.